I did the study. Field sense, there's no way you're going to do that.
Yeah, calculations apparently. Yeah.
You lost me.
It's also battling magnets. It's irrelevant. That's
It's
finished.
from the past.
Yeah, that's it. That was exactly.
It's in the.
Can we set fire to it?
A ceremonial celebration.
I don't see why not. I don't know that David needs it as a record, but
It does. Anyway, guys, welcome back. Hope you had a really nice little break and that the mid-year exams are a distant memory. It is come to my attention a little bit that we still need to finish off the previous PowerPoint from before the break since revision. So we've still got to go over UV and magnetism, and then we've got geology to get through as well. So a few things to get through.
Magnetism's in that one.
Sorry?
Is magnetism in that now?
Yeah, magnetism is on this one too. Yeah, a few things to get through. I remember having conversations with someone, and I don't know whether I was mentioning it in this room, about this picture that I had some issues with, because it says long wave UV on the left, short wave UV on the right. And my recollection was that scapolite fluoresces an apricot under long wave and not necessarily under short wave. So I went back and checked my pictures, and my pictures are definitely all labelled long wave purple and short wave apricot. And then I went and checked my stones and some stones here, and they all fluoresce an apricot stronger under short wave and a kind of a weaker response, or no apricot under long wave, which is a little bit interesting. So sometimes the results that are printed in tables, or the ones that are printed as your characteristic general result to expect, is not what you always get, and it sometimes depends on the unique chemical composition of a particular stone, and often from a particular location or a mine, and we don't always have that detailed information to be able to make those types of judgments based off simple ultraviolet light responses. But just to say that if we did discuss this previously, this photo is correct, and this particular scapolite in my collection at home fluoresces a strong apricot colour under shortwave. So we're going to go over ultraviolet light and the reactions that we can see. How many of us have started to look at ultraviolet light in the prac room? I think we all have. So we're all kind of a little bit up to date with how we do this procedural rise and what we need to write down. So we're just going to fill in the theory component of it. So not all minerals are going to fluoresce. There's only about 15% of minerals that fluoresce, which means that the vast majority of gemstones that we encounter are not going to show any fluorescence, which means they're going to be inert and most of the time not be able to be seen when we put them under the ultraviolet light, because they almost appear black against a black background. Sometimes though, the ultraviolet light does allow through a small amount of visible light and can illuminate some of the gemstones just enough to be able to see them when they're inside the viewing box. One of the things that we need to get used to is what is fluorescence as opposed to what are other observations that might be able to be made. So fluorescence is the visible emission of light when it's been subjected to a higher energy light source, and it's translated into a lower energy light source in the form of visible light that we can see. Before we get into that, we're going to do a little bit of revision on the atomic structure, what an atom is, And what is it about atoms that can cause fluorescence to happen? So we have an atom that is comprised of a nucleus, where the nucleus has got the heavier subatomic particles, being the protons and the neutrons. Neutrons having no overall electrical charge, and the protons having 1 unit of positive charge per particle. Surrounding that tiny little nucleus, we have a cloud of negative energy, which is comprised of electrons. And for each single electron, they carry 1 unit of negative charge. So 1 electron balances 1 proton to make the whole atom electrically neutral. Now, you might remember from when we did chemistry at the beginning of the year that these electrons arrange themselves into layers of energy levels, and we sometimes refer to those as shells. In addition to arranging themselves into layers and into shells, electrons tend to pair themselves off also. So some atoms may have a pair of electrons in the valence shell, and some atoms have a single electron in the valence shell. Just to remind ourselves of what the shells may look like in a very, very simple diagram, this is one way of representing an atom. There are more complex models that represent the behavior of electrons a little bit more accurately than what this model does. But for example, carbon has got 6 protons in the nucleus, and it's got 6 electrons surrounding it. So each proton is balanced with an electron, which makes the overall electrical charge of this carbon atom neutral. The innermost layer shell can have 2 electrons, which means that there are 4 electrons that will occupy the next layer out, the next shell out. But this atom wants to have 8 electrons in that valence shell, because we've got that octet rule that says that atoms are most stable when they have 8 electrons in their valence shell. So carbon wants to fill its valence shell and acquire 4 more electrons to make 8. So this is how we have bonding occur. And I'm going to just skip over that. Kind of said that as well. So some of these elements are going to have the ability to fluoresce when ultraviolet light is, shone on them. Now, ultraviolet light is a form of higher energy light source. So some of these elements transform a higher energy light source into a lower energy light source of visible light. And the elements that are going to do this are the ones that have an unpaired electron in the valence shell. We spoke earlier in the year about transition elements, and that these also have that unpaired electron in the valence shell. When light interacts with an atom, it's these unpaired electrons that react to that energy source of the light. Paired electrons requires too much energy to separate those electrons, but a single electron by itself is available to interact with light sources. So it's because there's so few elements in gemstones that have that unpaired electron, it's those transition elements. That's the reason why we only have 15% of minerals fluoresce. Now, not all transition elements actually produce fluorescence. Some of them actively stop fluorescence from happening. Notably iron, which is a transition element, iron actually suppresses and stops fluorescence from happening. So it's not every element that has the unpaired electron. So just again, fluorescence is where the emitted light, or the colour that we see, occurs at a longer wavelength than the light that is actually interacting with the stone. And the longer the wavelength is, the smaller the amount of energy that that light contains. So we have a high energy light source in ultraviolet light, and then it's transformed into a lower energy light source. So this implies that some of the energy might be lost, but the laws of physics say that no energy can be lost. So what's actually happening is that some of the energy is being transformed into other types of energy. So instead of it all being kept in as light energy, some of it is transformed into vibrational energy and some of it's transformed into heat energy. So we've still got that conservation of energy, that no energy is lost from the system. But this is what also contributes to the fluorescence, that kind of breaking down of the energy and dividing it between different properties of that gemstone. Now we can go into a lot of details about the behavior of the electrons, and there's still a lot of details that is unknown about the behavior of electrons, but the study of electrons is referred to as quantum mechanics. And there was a quote that I was reading only a couple of months ago that said that if you think you understand quantum mechanics, you don't. And that's from one of the leaders in the field who openly says he doesn't understand it. Anyway, so what happens when an object fluoresces? The light is interacting with this unpaired electron. The light interacts with the gemstone, and as the ultraviolet light passes through the gemstone, it interacts with that unpaired electron, and that unpaired electron takes on a parcel of that energy from the light source. It's a very specific size parcel of energy, and each individual atom that has an unpaired electron takes on a very specific parcel of energy that is a different size to another type of element that might be also accepting parcels of energy. That parcel of energy is the right amount of energy that's required to raise that electron up into a higher energy orbit. So that electron jumps up into the next electron shell, which is currently vacant and unoccupied. But the electron can't maintain that level of energy, and it drops back down to what we call the ground state in the valence shell. And it does this very, very quickly in a fraction of a second. So the parcel of energy that it takes on lifts it up to a vacant shell, it drops back down, and it releases that parcel of energy again. That parcel of energy is released as light energy, but also as heat and vibrational energy. So when we take out the energy that's associated with the heat and the vibration, then the light energy is a much smaller energy component, smaller energy level, which corresponds with a longer wavelength, which corresponds with visible light being seen in the gemstone. And this is what we see as fluorescence. So a gemstone may fluoresce red, it may fluoresce orange, on rare occasions it may fluoresce green, and those colours that we're seeing are the result of the very specific size of the parcel of energy that's being released back to continue travelling through the gemstone. So I think I've said all of this. So the electron accepts the parcel of energy, but releases it almost immediately. So it jumps up to the higher orbit, back down to the ground state, releases the excess energy as light, vibration, and heat. The amount of energy released depends on the atom. So this is really, really cool because it means that the same atoms, because they take on the same size parcel of energy, regardless of what gemstone they might be in, are likely to cause the same colour of fluorescence. So we can see patterns based on the chemistry. So for example, chromium will fluoresce red. So it doesn't matter whether the chromium is in ruby or whether the chromium is in spinel, it's still going to fluoresce red because the chromium atom itself takes on a very specific size parcel of energy and then releases a very specific size parcel of energy that results in the red light being seen. The process for fluorescence is very, very quick. It's a fraction of a second, 10 to the minus 8 of a second to occur, and it continues continuously while the light source is turned on. So these little electrons are continually jumping up and down many, many times per second, accepting parcels of energy, releasing parcels of energy, which gives the appearance of a constant colour being emitted from the gemstone. So it glows while the light source is turned on. Fluorescence though, standard fluorescence stops the minute the light source is turned off. So we don't expect to see that light emitted continuing beyond when the light source is turned off. But there are a few exceptions to that. Gemstones can phosphoresce, which is the slow release of energy back down to the ground state. So the light that is emitted continues for a couple of seconds after the light source is turned off. That's a fairly rare occurrence with gemstones. It's not seen very frequently. It is seen rather predictably with opals, and it can also be used to separate synthetic diamonds from natural diamonds, particularly the HTHP synthetic diamonds will phosphoresce. I think I'll skip over that slide. Oh, there you go, phosphorescence. Slow emission of light from the excited state back down to the ground state, taking 1 second or longer.
Is that because they're spheres, so the light is sort of bouncing off in it?
Not necessarily. It's a very, very complicated part of quantum physics, and it depends upon how many steps the electron takes to drop back down to the ground state and how long that process happens. So the opal is not because of the spheres of silica, but it's just other parts of the chemistry of the material and the elements that make the opal up.
Does phosphorescence happen much in crystalline substances?
Diamond is one of the most notable ones, and the synthetic diamonds, the HTHP synthetic diamonds. So where an opal may phosphoresce for 6 to 8 seconds, I've seen some HTHP synthetic diamonds phosphorus for 5 minutes or longer. I've got a video of one that I took during a class, and I stopped videoing it after 5 minutes because I thought there's no point continuing to video this phosphorescence. It's going. But it's rare to encounter phosphorescence in a mineral. Yeah. So both fluorescence and phosphorescence come under the umbrella term of luminescence. We tend to say phosphorescence, but phosphorescence is just one type of luminescence, and we can't forget about the phosphorescence. Now, whether an item is going to fluoresce or not fluoresce will depend upon whether there are activators present within the crystal structure. And the activator is an atom that has an unpaired electron in its valence shell, but not all atoms with unpaired electrons will act as an activator. The elements commonly include manganese in some circumstances, chromium, titanium in some circumstances, copper, lead, europium, cerium. Some of these are not frequently encountered in gemstones. The ones that are frequently encountered in this list that are going to be more important to us, we have the chromium, produces really, really nice red fluorescence in gemstones such as ruby and in spinel. And nitrogen is responsible for the blue fluorescence in the natural diamonds. And because there's a lack of nitrogen in the synthetic diamonds, we don't get the blue fluorescence in the synthetic diamonds. Diamonds can be very, very, very complicated with their chemistry and what causes fluorescence, and we can see a whole range of other colours. But nitrogen in the diamonds is one of the key components. Yeah. So manganese can be responsible for red or orange fluorescence in calcite. However, manganese also produces an orange colour in spessartine garnet, and in spessartine garnet it won't fluoresce. So it's not reliable in causing fluorescence in every mineral that it is present in, but may fluoresce in some minerals. Uranium is responsible for green and yellow and green reactions in some minerals, but uranium is a very, very, very rare element and is not usually found in most of the gemstones that we're going to be testing. Chromium is responsible for the red fluorescence that we see. We see it in ruby and spinel, which are red gemstones, but chromium is also responsible for the green colour of the emeralds, and emeralds that are rich in chromium will also fluoresce red. The synthetic emeralds are much more likely to show a strong red fluorescence because they have got a lot more chromium present and they haven't got any other elements that might act as a quencher. So natural emeralds tend to have a mix of iron in there as well, although the main cause of colour is chromium. But elements such as iron act as a quencher and will deaden or destroy any fluorescence that is happening. Zircons typically fluoresce a type of yellowish colour that we typically refer to as a mustard fluorescence. And this is due to lanthanides such as terbium and dysprosium. Now, this is one of those things that can come down to country of origin. In Australian zircons, there isn't enough lanthanides to cause a fluorescence. Am I saying that right? I'm suddenly second guessing myself there. I know in Australian zircons you won't see the zircon line with the spectroscope, but I'm pretty sure they don't fluoresce the mustard colour as strongly as the overseas ones either.
I'm going to go home and test.
I'm going to go home and test. Now that I've opened my mouth and put the foot in it and gone, I'm reaching back to the back of my head and pulling out a bit of information. So the activator works because of an unpaired electron in the outer orbit of the atom. Quenchers, however, do something a little bit different. Sometimes I like to think about quenchers as playing hot potato with the energy source. They transform all of the energy source into vibrational energy and into heat energy and don't release any of the energy in light energy. So when the quencher is present, you won't get any fluorescence, or it'll dampen down the fluorescence from other activators that are present. The best known quencher for gemstones is iron, but depending on the type of mineral and the crystal lattice and the structure, copper and nitrogen can also act as quenchers. So they can be activators, they can be quenchers depending on the structure. So it all gets very, very complicated. But generally, because most of the coloured stones that we handle, a lot of those coloured stones have got iron in the crystal structure. Most of them are coloured by iron. If they're a yellow colour mineral or green colour mineral, garnet being a red colour mineral, coloured by iron, all of these minerals will be inert to ultraviolet because iron is such a strong quencher. Now we use two different sources of energy for ultraviolet light, and we call those long wave and short wave. And that's based upon which one has the longer wavelength and which one has the shorter wavelength. So the long wave ultraviolet light is 365 nanometers and the short wave ultraviolet light is 254 nanometers. A quick way way to try to remember this is to remember how many days in the year, 365, and then to subtract 1 from each of those numbers, or minus 111, 111 from the long wave, to get what the short wave is. If that works for you, then that's a bonus. We do need to remember what the long wave and short wave light sources are. Another thing that I might mention is that because of LEDs, there are a lot of other options now creeping onto the market for use in ultraviolet light. The machines that we've got in the lab are tubes rather than LEDs. And the LEDs, there's a lot more other options. You've got to be really careful if you're buying some ultraviolet light sources for yourself at home, because if it's not the right wavelength, it may still give you a fluorescent response, but it's going to be inconsistent with tables printed for that gemstone. So it may not give you any diagnostic evidence that you're looking for, because the energy of the UV light source is going to be different, which will result in a different output from the stone potentially. Recently, for diamonds, they're using an even shorter wavelength. They're calling it a deep UV or something. De Beers has got the deep UV, and John Chapman's bringing out his own version of that. And that's really good to show the growth structure of the crystal for diamonds. So depending on what you're reading, you may come across other wavelengths that are useful for gemology. But the standard two that we use is the long wave and the short wave.
They're also talking about blue laser, like blue laser pointers as well. Yeah.
Yeah, the blue laser pointers. So the 405 nanometer lasers can be really, really useful. And the 405s have also been proved, there's been a lot of research being done into synthetic diamond screening using a blue laser for the 405 nanometer. A bit of safety discussion, because ultraviolet light can pose some dangers to us. The lamps that we have in the lab are contained within a viewing box, and that viewing box has got a little window that we look through, and that little window has what's called a Woods filter, which filters out any of the harmful ultraviolet radiation from reaching our eyes. So we can safely view the gemstone without looking into the ultraviolet light and causing us damage. We need to be a little bit careful that we don't look inside the box from the side while the door is open, because there's no safety protection for our eyes when viewing it that way. So don't look inside the box from the side. Prolonged long wave ultraviolet light can form cataracts, so we need to be very cautious about that. And prolonged shortwave ultraviolet light can sunburn your eyes and cause something called welder's blindness. Now, on the long wave ultraviolet lights, at the moment on the, to be able to purchase, there isn't a dedicated shortwave ultraviolet light that provides a narrow emission spectrum. There are shortwave LEDs, but they have more of a range of spectrums. So they're not suitable for gemology yet, which is why you guys haven't got one in your kit. But you do have a long wave ultraviolet torch, and there are other units that you can buy on the market as well. Not all of the long wave torches that you buy have got the specific 365 nanometer that we want to use, and all of them have got slightly different energy outputs. Now, the one that you've got, which is called a Convoy S2 Plus, which is the black one in your kit, that is fitted with a Woods filter to reduce as much of the harmful UV that comes out of that torch. But it's still a very powerful light source, and it can still cause a lot of damage to your eyes. So please do not look directly into your Convoy light, because we don't want any eye damage. It's a very, very powerful little light. And you may at times notice if you've got it close to a gemstone that the gemstone appears to heat up from the energy from the light source. And you may even notice, though it's not doing the stone any damage, but you might notice a little bit of heat haze coming off the stone as well. Another thing is the ultraviolet light can cause, in some instances, temporary changes of colour to your gemstones. So you've got to be really, really careful with how you use that torch. I found out the hard way when I had a customer who brought in a gemstone in a stud mount, and their customer, because we're wholesale, we only deal with jewellers, the jeweller's customer had lost one of the earrings and they needed to replace the stone and make another earring. So first step was, what's the stone? Second step, can you supply another to match? And I knew it was zircon because it had doubling of the back facets, but I still wanted to check that it had mustard fluorescence. So I stuck the long wave UV torch on it and turned this really beautiful blue zircon into a really yucky, dark, murky green that did not reverse itself for the next 4 hours.
And Argyle diamonds are the same.
Ooh, yes, I've heard that Argyle diamonds can also do that as well.
And they don't revert on their own. You have to put them under a special blue light.
Yes, yeah. So there's a number of gemstones that could potentially change colour. Sometimes the change may be permanent, sometimes the change may be temporary. With the zircon that I played with, it was lunchtime on a Friday, and I stuck it in the safe over the weekend, and when I came back on Monday, it was the original blue colour, and I was like, that was a near miss. And then I thought, I want to experiment, so I took out every blue zircon in my collection to see how many of them did it. So with those long wave torches, because they have a higher energy output, to get the same effect as the box that we use in the lab, we should keep it about 30 centimetres away from the gemstone that we're testing. The closer we get, the more energy we're going to give the stone, and the brighter the fluorescent effect is going to be. That's also really important to remember, because sometimes we use fluorescence, the strength of the fluorescence, is it weak or is it strong, to try to help us decide if the stone is natural or synthetic. But these new torches on the market are so powerful that they're supercharging the results that we're seeing with the fluorescence. So at times we could misinterpret the strength of the result as being a synthetic result when the stone's actually natural. So to be able to compare it to what we're used to seeing in the traditional boxes, keep the torch about 30 centimetres away. Because about 15% of minerals fluoresce, the test can be limited as most of the gemstones are going to be inert, but it's also a really good little test for screening parcels of stones that are a similar colour. So if you've got a parcel of stones that may include almandine, garnet and red spinel, pass the UV torch over and pick out all the ones that fluoresce red, because they're not going to be the garnets. When I was putting together the spectroscope sets a couple of years ago, I had a parcel of synthetic pink stones that I got from my boss that he said, pick out whatever you want from that. And I was wanting pink CZ. Pink CZ under long wave fluoresces a really unnatural kind of greenish colour, like nuclear reactor green, whereas the pink sapphire, which was also in the mix, coloured by chromium, fluoresces red. So passing the long wave torch over, I picked out all the green ones from the mix because I knew they were going to be cubic zirconia, and it was the pink cubic zirconias that I was wanting. So there are at times useful applications for screening parcels of mixed stones. Yeah, so colour seen under UV can separate a parcel of mixed stones of the same colour. Knowledge of chemical composition of gemstones and activators is going to be really, really useful for you, because knowing that the almandine garnet is coloured by iron and is inert, and knowing that the spinel is coloured by chromium and will fluoresce red, is the knowledge that you're applying when you try to separate a parcel of stones that look similar in colour. But it's not the most useful test, so it's a screening tool, but it's not necessarily something that we rely on identification for. Most reliable instruments for identification, hand lens with inclusions, but optical tests such as the refractive index of the gemstone. And we need at least 3 or 4 different tests to come together to verify the identity of the gemstone. We never rely on one test in isolation. I'm just going to skip over that a little bit. Chromium's a strong activator. Burmese rubies have high chromium content. Most synthetic emeralds and rubies will fluoresce quite a lot because they have lots of chromium in them. Some other interesting things, yellow sapphire from Sri Lanka will fluoresce apricot. That allows us to separate it from yellow sapphire from other sources and from synthetic materials. And as far as I know, they still don't know why it fluoresces an apricot colour. There's still a lot of research being done in gemstones, and there's not always the funding available to track down every answer that we want to know.
Maybe Sri Lankans like apricots.
Maybe. Natural opal will phosphoresce for 8 to 10 seconds, whereas the synthetic opal will phosphoresce for maybe 2, 3, 4 seconds. So synthetic opal, blink and you miss it, but you will notice a phosphorescence. The natural opal should phosphoresce for longer than 2 blinks, depending on how fast you blink. Scapolite can be separated from quartz because of its fluorescence. Quartz will never fluoresce. It's got too much iron in it and there's no other activators present. The scapolite usually reliably fluoresces that apricot colour. Scapolite and quartz can overlap in refractive index and specific gravity. So we've only got 2 tests to separate them. One is the optic character and the optic sign of the material. They're both uniaxial, but the quartz is uniaxially positive and the scapolite's uniaxially negative. The quartz is inert and the scapolite fluoresces. And apart from that, all other test results may be identical. So scapolite can be a little bit tricky to try to identify. Always record down the colour that you see. And ultraviolet light sometimes has quite a lot of violet colour light in it as well. Not all of the visible, it sometimes contains quite a large amount of visible spectrum light in the purple-violet range. So occasionally we may notice a purple reflection from the surface of the gemstone rather than a purple glow due to fluorescence. And this is the reflection of the ultraviolet light rather than fluorescence itself. So we need to attune our eyes to recognize when it's only a reflection and not fluorescence. Okay, so going through a couple of photos, synthetic cobalt blue spinel. This one here is fluorescing red under long wave light. It's usually contaminated just a little bit with chromium, so the red fluorescence is actually from chromium, not from the cobalt. And it's usually under short wave, shows a chalky blue fluorescence. And those are fairly reliable for synthetic cobalt spinel. Natural diamond will usually fluoresce blue, but there's a lot of colours that it can fluoresce, yellows and greens. The natural material is stronger under long wave and weaker under short wave. Some of the synthetics may be reversed and be stronger under short wave and weaker under long wave, but that's not for tonight's discussion. Damburite can show a blue fluorescence to both long wave and short wave. Funny story, I've got about 10 dendrites in my collection at home, which I collected 15 to 20 years ago. All of them fluoresce blue, and these are pictures from my own collection that I've taken at home because that's the kind of thing that I like to do on Friday night. Anyway, I'll give you a hint, none of the dendrites in our collection fluoresce at all. So I went and tried to buy dendrites over COVID to put into the ultraviolet test collection. And I must have bought 15 or 20 dendrites and none of them fluoresced. So there must have been one deposit about 15 or 20 years ago from one location that produced dendrites that fluoresce, and the current producing locations do not fluoresce, which is really annoying if you want to buy a dendrite that specifically fluoresces. So this is a possibility, it's not definitive. Scapolite usually fluoresces an apricot colour. Apparently, most of the ones that we have in the collection are stronger under shortwave, and the notes say that it's seen under long wave. So again, maybe differences in country of origin and deposits. The Sri Lankan sapphire with the apricot fluorescence, under long wave, stronger, short wave, weaker. Most gemstones will usually show a stronger response to long wave and a weaker response or inert to short wave. Just for fun, this is a corundum doublet. Now the crown is composed of an Australian blue sapphire, which is rich in iron, which means it is inert, but the pavilion is a synthetic sapphire that often shows a chalky bluish white response. So when we're testing stones, we need to make sure we turn the stone and view it from the pavilion as well as from the crown, because from the crown, this stone could look completely inert. This one actually does show a little bit of a border of that chalkiness around the crown, but there are some stones that you won't see the reaction from the different material unless you turn it over. GTD, again, the almandine garnet is iron rich, so it is inert, but the paste is, in this case, fluorescing a chalky green type of colour. And you might notice this band across the top of the crown of the GTD has got a kind of purplish glow. It's not fluorescing, that's the reflection of the ultraviolet light source in the crown of the gemstone. So just watch out for that purple reflection. Okay, on to magnets. Magnets are lots of fun, but they pose a few challenges for us in the working environment as well. So we need to treat them with a little bit of care and maybe be a little bit scared of what they might do.
My pacemaker.
Oh, okay. Anyone got a pacemaker, by the way? If you have a pacemaker, these neodymium magnets are very, very strong and can interfere with pacemakers. So keep it away from any medical devices. Keep it away from mobile phones and computing devices because it could clear the memory of your computer and scramble it. So the magnets that we are using in gemology are called rare earth magnets or super magnets, or neodymium magnets. The neodymium is the rare earth element that is used to produce these magnets. They're very, very, very strong magnets. They're sometimes sold in sets, and they're so strong that they can fly at each other over a distance of 10, 15 centimeters, and they can crack the nickel casing that they have, so we have to be a little bit careful. Most of the gemstones that we deal with are not magnetic at all, but a small proportion of gemstones may acquire magnetic properties when they come into close contact with supermagnets. Supermagnets have only been around for a couple of decades, so this is kind of a new little toy for us to play with in our toy kit when looking at gemstones. Generally, gemstones will be slightly magnetic if they contain elements such as iron. A lot of gemstones that are rich in iron are going to respond really, really nicely to a magnet and show some weak magnetic properties. The gemstones, though, are not actually magnetic, and once the magnet is removed from the gemstone loses any of its magnetic properties. Neodymium magnets exhibit a very strong, may fly at each other, so we've got to be careful of that, careful of mobile phones, computers and pacemakers. Anything that is metal, they will be very strongly attracted to. So depending on the tables that we're using, the structures underneath the tables, the magnet may be attracted to and kind of naturally roll or fly in that direction. Sometimes they may snap in that direction while you're even holding them, and that kind of can be surprising a little bit. Where we have to be careful though is with tweezers. Our tweezers will often fly at the magnet if they become kind of get in close proximity with the magnet. If we're holding tweezers with the gemstone in and we get the magnet close, it will snap the arms of the tweezers together, and it could cause damage to the gemstone if it crushes the gemstone. At any rate, it'll force the tweezers to go snap, and the noise from the tweezers will make you jump. So a little bit of fun, potentially. We also have other metallic items on the desk, such as the polariscope and sometimes the refractometer, depending on your workstation at home if you have a refractometer. And if you're holding this in your hand and your hand happens to wander, it will snap onto these metal objects.
Can I just add, it will take the paint off your refractometer, the paint off your polariscope, the paint off any metal filing cabinets it becomes attached to. Please be careful.
Yep.
This is seriously amazing.
Even our little tiny ones that we have in our kit.
Yep.
Oh yeah.
They are very, very, very strong little magnets.
I mean, you can experiment at home. Just be nice to the lab.
So with gemstones, the gemstones that we're going to notice a magnetic response are going to be gemstones that contain large amounts of iron or large amounts of manganese and large amounts of rare earth elements. So there's not a lot of natural gemstones that contain rare earth elements, but some of the synthetic gemstones, particularly cubic zirconias, and some of the synthetic garnets, there's materials on the market called YAG, yttrium aluminium garnet. Yttrium is a rare earth element. They're very magnetic. They also have other rare earth elements in their composition that they use to produce the colours. So things like CZs, YAGs, and GGGs, gadolinium gallium garnets, can be magnetic. Iron, although iron is present in a lot of gemstones, most of the gemstones, the iron is not in the right structure and not enough of it to produce a magnetic response. So it's still a kind of rare response that we see. Most of the dark green or black gemstones will show a magnetic response. So things like black spinel, black tourmaline, black star dioxide are going to show a strong response, and garnets, because of the high iron content, are going to show a strong response. Garnet is the only gemstone that will actually be picked up by a magnet. The others will drag.
What about the peridot? What's in peridot?
Peridot, it's iron,
Okay.
and it won't be picked up, but it may drag depending upon how much iron is present in the stone. Manganese, we've got garnet, spessartine garnet. Manganese is actually stronger in its magnetic response than iron is. So it's not uncommon to see spessartine garnet jump almost a centimetre towards a magnet and then be picked up, whereas an almandine garnet typically won't jump to the magnet, but can be picked up fairly easily. So members of the garnet family. Garnet is a very complex group of related minerals, related by a similar crystal structure, which means they exhibit solid solution. So it depends upon the amount of iron or the amount of manganese that's present as to the size of the response that you're going to see. It's also dependent upon the size of the stone. Larger stones are heavier and may not be able to be picked up by the magnet because the magnet might not have enough strength to pick it up. So it just depends on the size of your gemstone. So black spinel, black diopside, black tourmaline contain a lot of iron. They'll all show a very strong response. Rhodonite and rhodochrosite, which are your ornamental stones, will show a response because of the manganese. But in the faceted gemstones, it's spessartine garnet that's coloured by manganese that is going to show a response. Manganese also contributes to the pink colour of the morganite, but there isn't enough manganese present to produce a response in morganite. And HTHP synthetic diamonds may show a magnetic response, particularly early production, because of the equipment that they use to grow the diamonds in, contains magnetic metals, which are then incorporated as inclusions into the diamond structure. Most of the production of synthetic diamonds, especially over the last 5 years, they've perfected the process to the point where they can grow very large crystals and inclusion free. So because there's no inclusions, you don't see the magnetic response. The gemstone has to be I1, I2 or worse to see that magnetic response in the HTHP diamonds. Some of those synthetics, CZ, YAG and GGG. Factors that affect observation. So we've talked about solid solution, where we can have one element that can replace another within the chemical formula without changing the external shape of the crystal. Was that a question at home? No?
No, I posted a link to a website.
Ah, that's okay. Thank you. The size of the gemstone. So even though almandine garnets may reliably pick up with your magnet, a large almandine garnet will not pick up with the magnet. And it's not necessarily a quantifiable test. So I can't tell you for your particular magnet what the cut-off carat weight is that the stone's going to pick up or not pick up. But through experience, you know, a smaller stone, a carat, may pick up easily. Larger stones, 3 or 4 carats, may not pick up but may still drag. But they'll get to a size where they won't even drag because the stone's too heavy. Now, other factors that affect their observations, we've got the surface friction of the desk and the surface area in contact with the magnet. So when you are testing your stones with the magnet, we need to try to minimize the surface friction of the desk. So we're not going to place the gemstone table down on our working area because that's a very large facet in contact with the desk. Instead, we're going to turn it over onto the pavilion where we've just got one very small facet. So we've got a smaller surface area. So we're going to reduce that amount of friction and you'll find that it will drag easier. And if you want to play around, if you've got a gemstone that drags when it's resting on its pavilion, turn it over to the table and see if you get the same response. Quite often you won't get the same response when the stone's on the table, and it's just because of that friction. The surface area in contact with the magnet, the larger surface area we have touching the magnet, the stronger the power of the magnet is going to be. So while we've got the gemstone resting on its pavilion, we've got the table being presented to us. So we take the flat end of the magnet and we touch it up against the flat surface of the table, and that maximizes the amount of the magnet in contact with the gemstone. and is going to show us the strongest results. So procedure, ensure the gemstone is clean and dry. Place the gemstone on the desk resting on the pavilion. And then you bring your hand in holding the magnet with the end of the magnet aimed towards the table, and you approach slowly, because if you have an orange gemstone that happens to be a spessartine, you want to see that gemstone jump towards the magnet. If it's going to jump, you have to move slowly and kind of come a couple of millimeters away from the stone so you notice any of that movement. If it doesn't jump, you place the magnet against the table and you see if the gemstone will lift. And if the gemstone doesn't lift off the table, you slowly pull your hand away from the gemstone and see if the gemstone sticks to the magnet and travels with you and drags across the table. If it won't drag across the table, it still may show a weaker magnetic response. And what you would do is have the magnet only a millimeter or so away from the gemstone, so not touching the gemstone, but move the magnet around the girdle of the gemstone. And you might notice that the gemstone turns and follows the magnet very, very slightly, and it might wiggle a little bit. But you're not going to notice that movement if the magnet's up close against the gemstone. You want to see if it's going to move in response to the magnet being close. So you've got a very strong response when the gemstone jumps to the magnet. You've got a strong response if it drags with the magnet. You've got a weak response if it kind of wiggles with the magnet. And then you've got no response if it does nothing. Anyway, end of lecture. Any questions on magnet or UV? Excellent. 8:26, that's okay. We're going to jump into geology. Okay, so tonight's lecture on geology, we're going to be covering really quickly the structure of the Earth. We're going to be spending time talking about classification of rocks, so potentially looking at the chemistry of the rocks, the amount of silica that they might have. We're going to talk about the rock cycle, how rocks are produced, and we're going to talk about 3 different classifications of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. We're going to talk about hydrothermal processes and something called pegmatites, pegmatite being a very specific type of igneous rock. And then we're going to talk about weathering and secondary gemstone deposits, so things like gem gravels. Starting off with looking at the structure of the Earth. The Earth has got different layers within its structure. And if we peel back those layers, we can kind of think about the Earth as being a little bit like an onion. Yay, someone's listening. I got a laugh. So essentially we've got the atmosphere surrounding the Earth, the oxygen that we breathe. What we stand on, the ground that we stand on, is referred to as the crust. And we've got continental crust and we've got oceanic crust. So the crust that's beneath the water, the ocean, and the mountains, which is the continental crust. Underneath the continental crust, we have a layer of mantle, and underneath the mantle, we've got the core. So we've got 3 distinct zones within the Earth's surface. And then the core is also broken up into different layers, and the mantle is broken up into different layers, and the crust can also be broken up into different layers. For the benefits of your end of year exam, you do not need to know the layers of the Earth or the thicknesses of the Earth and some of these words. But I've thrown them in just for your benefit, because I thought you'd like to know about them. So we've got the atmosphere, we've got an outer silicate crust. So the ground that we walk on is mainly silicate based. So remember earlier in the year when we were talking about Mohs scale of hardness and the importance of hardness 7, said quartz has hardness of 7, so anything softer than quartz can be scratched easily. 70% of the Earth's crust is made up of silica-rich minerals, most of which is quartz, which has a hardness of 7. So the Earth's crust is silicate-based. So that's something to remember. The mantle is highly viscous. So that means that it's got a very fluid, but very slow-moving fluid molten rock. The liquid outer core is also viscous, but much less viscous than the mantle. So the plastic flowing rock moves a lot slower in the core than it does in the mantle. And the very, very, very inner core is believed to be solid. The core, what we know about the core, because we haven't been able to drill that far down to be able to test it, but through seismic measurements, we know that the core is made up mainly of iron and nickel. I hope it's nickel. Again, yeah, okay, phew, nickel. And it has a radius, the inner core has a radius of about 1,200 kilometres. I don't know these numbers either. I'm going to read off the slide. And the liquid outer core has a radius that extends to 3,400 kilometres. And it's believed to be comprised 80% iron and nickel. 4.5 billion years ago, when the Earth was forming, we had a lot of molten elements. And they went through a system called planetary differentiation, whereby those heavier elements migrated and found themselves at the center of the Earth, and the lighter elements found themselves in the outer layers of the Earth's structure. These are not concepts that you need to be aware of, so you don't need to tell us about planetary differentiation at any stage. What I do want to point out, though, because it is kind of important, is where the gemstones form. So they don't form in the core, and they don't form in the lower parts of the mantle, but they tend to form in the crusts and in the uppermost part of the mantle. The crust extends from a thickness that can be as thin as 5 kilometres under the oceanic crust area, but it can be up to 70 kilometres thick under the mountain ranges. And the gemstones are going to form in an area that's about 40 kilometres deep within the Earth's surface and can extend at times into the uppermost part of the mantle. So we're just looking at the silicate-rich crust for where our gemstones form. The mantle extends to a depth of almost 3,000 kilometres and is the thickest layer of the Earth, and it's also comprised of silicon rocks that are rich in iron and magnesium. And the iron and the magnesium produces rocks that are very dark in colour. The mantle, the upper mantle is called the ionoasthenosphere. It's composed of plastic flowing rock that's about 200 kilometres thick. And the uppermost part of the mantle, the lowermost part of the lithosphere, is comprised of richard rock that is 50 to 120 kilometres thick. The important part, though, is the crust, because that's where all the action happens for our gemstones. So it varies in thickness from 5 to 70 kilometres. And that can be important for our gemstone producing areas. One of the things, and I know I'm going outside of the course notes for Gem 1, but just to try to breathe a little bit of interest into the concept of geology. When you study diamonds as diamond tech and you learn about where diamonds form. Diamonds require a lot of pressure to be able to crystallize. So you find them in areas of the Earth's crust where you've got a lot of very high mountain ranges and you've got a lot of thick crust, because that thick crust produces the weight that produces the pressure. So we don't get any diamonds forming under oceanic crust, which is thinner, because they don't get the pressure to form the diamonds. Diamonds are a little bit different to other gemstones, but just to highlight that the thickness of the crust can be important into the growth of gemstone materials. Oceanic crust, being the thinnest, is comprised of dense rocks rich in iron, magnesium, and silicate. And they tend to be basalts, and they tend to be a very dark brown colour. Continental crust, though, is less dense and is comprised of rocks rich in sodium, potassium, aluminium, and silicate. And these rocks tend to be granites. Granites are a combination of quartz and of feldspars. So we have silicate being in quartz, but the feldspars are also silicate-based minerals with potassium and sodium. So these are all components of rocks. These elements combine together to form particular minerals, which then come together to form particular rocks. Granite being one of the most important ones of the continental crust. Now, some of these words here you may come across. Basic or ultramafic rock refers to rocks that have a very low silica content. And in addition to being a very low silica content, less than about 45%, basic rocks or ultramafic rocks tend to have no free silica. So we don't tend to find quartz crystals in ultramafic rocks. Where we've got rocks that have got a high silica content, we call them acidic, and they tend to have free quartz or quartz crystals in. Ultramafic rocks tend to have magnesium that's in excess of 18% of that rock. We've got high iron content, but we generally have low potassium content. And these rocks tend to be very, very dark coloured rocks. And they tend to have, because they don't have much free silica, we don't get any of the silicate minerals or crystals forming in these rocks. Now, the formation of the gemstones, most of the gemstones require a rock environment that is high in silica content. And when we talk about pegmatites later on during the discussion, we also require an aqueous environment as well. We have hydrothermal growth processes that require fluids and water to be present. But the formation of gemstones generally takes places in the crust and in the upper layers of the mantle, generally at a depth of around 40 kilometres. So when we start getting into different types of rocks and the rock cycle, we're going to have to remember that most of these gemstones form at depths of 40 kilometres beneath the Earth's surface. So we need actions of plate tectonics to be able to bring these gemstones up to the surface to areas where we can access them, either by mining them or finding them in river systems. So gemstones are comprised of elements that are combined under the right conditions of heat and pressure to be able to grow a crystal. They also need enough room to be able to grow as well. So all of these factors are very, very important. They also need enough time to be able to grow large crystals. So time is very, very important. Room to grow is very important, and the temperature and the pressure is very, very important. The elements that comprise our gemstones are not necessarily rare, although some of the transition elements and some of the rarer elements can be more rare, but most of the elements that comprise our gemstones are not necessarily rare, but the conditions need to be right to bring them together for them to be able to form a crystal and grow a crystal. Some of the more common elements that we encounter in gemstones, we have carbon, which we find in diamond crystals. Alumina, Al2O3, by itself is corundum, but alumina or aluminium oxide may be present when combined with other elements to produce other gemstones. For example, spinel is magnesium aluminium oxide. So the crystal structure and the gemstone that we get depends on which elements are present and the way in which they arrange themselves in the crystal lattice. Silica, silicon dioxide, will form quartz crystals, but we probably remember maybe from the chemistry class that we looked at classifications of minerals based on whether they are silicates or whether they are oxides. And we could probably name a couple of other gemstones that are classified as silicates. So we know that combining silica with other elements gives rise to different types of minerals. And we've also got then the structure and the symmetry of how those elements arrange themselves into the different shapes of the different crystal lattices. Other elements that we encounter fairly frequently, magnesia, so magnesium, sodium and potassium are also found fairly frequently in gemstones. So these elements are not rare, but combined together under the right conditions with the right temperature and the right pressure and given enough time, they'll come together to form really beautiful crystals. So now we're going to talk about the rock cycle, which is going to lead to the formation of gemstones. And basically for the rest of the lesson, we're going to work on understanding this picture and describing this picture. And this picture is a summary of everything that you need to know from the geology class. So if you can describe and explain this picture, you'll be fine for the end of year exams. So this picture is a diagram of a portion of the Earth's crust and showing a portion above the Earth's crust as well. And there's a lot of different things that are going on in this picture. If we start at the bottom of the picture, then we have an area of magma. So magma is coming from beneath the Earth's crust, but at times it may rise up through the Earth's crust when conditions are right, and it takes advantage on existing cracks within the Earth's crust, or it might come up through a volcanic channel through to the Earth's crust. So we've got the magma. We can see here that the magma has got a little channel coming up through a mountain that has some black plumes through the top, so that's obviously going to be a volcano. Surrounding the magma is rigid rocks. And these rigid rocks here with the kind of fawn pale pink colour, we're being told here that these are igneous rocks and that they are also intrusive igneous rocks. So essentially magma, which is liquid or highly viscous, so it's a plastic flowing rock. As it cools down and solidifies, it forms rigid rocks, and the name of those rigid rocks that result from the cooling magma are called igneous rocks. So an igneous rock is any rock that has been formed by cooling magma. If that rock has cooled down beneath the Earth's surface, it's called an intrusive igneous rock. And if that magma cools down above the Earth's surface, it's called an extrusive igneous rock. And there are some basic differences between extrusive and intrusive igneous rocks. The intrusive igneous rocks are protected by the other surrounding rocks, and they take a long time to cool down. So they've got a lot of time to crystallize, and they tend to grow larger crystals, and the structure tends to be coarser. The extrusive igneous rocks, because they come into contact with the Earth's atmosphere, or they come into contact with waterways, they cool down very, very quickly. If a volcano erupts under the ocean quenches that magma and it solidifies a lot quicker than it would if it was seeping through existing rocks within the Earth's surface. So because of that time factor, time was one of those contributing factors on the previous slide. The quicker the rock solidifies, the smaller the crystals are going to be. So we don't expect to find large crystals in basalt. Basalt is a form of extrusive igneous rock produced from volcanoes. But because it quenches very quickly, and because magma is silica rich, then we get volcanic glasses found in that basalt. So we get obsidians. And we get obsidian because the time hasn't been long enough for that silica to arrange itself into a nice little crystal lattice. So instead of it being crystalline, it's non-crystalline. So once that extrusive or intrusive igneous rocks, once these rocks form, they can be changed to other rocks. They can be changed through a number of different processes. If we follow this circle around on this picture, then from the volcano, we go into like a weathering process. So one of those processes can be weathering of existing rocks. So that's where we take existing rocks, and through the process of wind or water, they're broken down into sediments, and those sediments are relocated elsewhere and then are laid down in layers and compacted over time and form new rocks. And those new rocks that are formed are called sedimentary rocks because they're formed from sediments of other pre-existing rocks. The other way in which rocks can be formed is from changing existing rocks. So it might be changing sedimentary rocks, or it might be changing igneous rocks, but through geological events that impose pressure and can heat up the rock, we can change the nature of the rocks. And these are called metamorphic rocks. So metamorphic rocks are rocks that have been changed through the action of heat and pressure. And then we can, through plate tectonics, we can force the rocks back deep down into the Earth's mantle, remelt them and start the process again, and then create more igneous rocks to be born. So it's all a process of recycling rock material. So we're going to go through this in a little bit more detail over the next few slides, but that's the process that we need to know. So rocks are classified as either igneous rocks, rocks that are produced through the solidification of magma, sedimentary rocks, rocks that are produced by the from sediments of other types of rocks, and metamorphic rocks, which are rocks that are produced through altering existing rocks through the actions of heat or pressure. And the rock cycle describes how existing rocks can be changed and form new rocks through a variety of processes, whether that's a weathering process or whether that's heat and pressure. And in that process, minerals and gemstones can be formed. So igneous rock is formed as the magma rises and cools. And as we know, magma is comprised of mainly silica-rich rocks. So it's not unusual to have a composition of magma that includes silica anywhere between 35 to 75% silica. And in addition to the silica, we have other elements present that can be combined together to form rocks. And it just depends upon the mix of chemicals that are present as to what type of rocks we're going to get from that particular body of magma. So it can contain aluminium oxide, it can contain iron, it can contain magnesium or calcium or sodium or potassium in addition to the silica that's present. And most of these elements, when combined, are going to form various types of feldspars. So feldspars and quartzes are the two most common types of minerals that we have in the Earth's crust. The igneous rock will be termed extrusive, where the magma is released by a volcano and where it cools down and solidifies on the Earth's surface. Or it's called intrusive, where the magma is solidified beneath the Earth's surface, which means that the magma is just seeping between existing cracks, but never actually makes it onto the Earth's surface, but cools and solidifies where it is within the structure of other existing rocks. On cooling, the magma forms other rocks and solidifies, and some of these rocks result in crystalline structures being produced as well. Where the silica is left over from that rock producing process, then some of our larger single crystals are able to be formed. So the large single crystals are the result of excess nutrients that are not incorporated into the rock forming minerals or the bedrock of the Earth's crust. So we get larger crystals of quartz, larger crystals of feldspar, larger crystals of olivine. Olivine, of course, giving us the peridot. Can be produced where we have excess silica from that rock forming process. And the particular gemstone that is produced depends on the chemistry of the magma that is rising in that particular location. And different locations are going to have different chemistries. Extrusive igneous rocks, because the magma can come in contact with air or seawater, the molten rock quenches very, very quickly. And when it quenches quickly, it freezes the silica content in its place, and the silica doesn't get a chance to lay itself out in those nice little lattice framework of a crystalline gemstone. So when it freezes not in a lattice framework, we get a non-crystalline material, and the gemological name for a non-crystalline material comprised of silica is glass. So we get glasses forming in the basalt. So this is where we get gemstones like obsidian. Volcanic rocks are usually very fine grained because there's not enough time for large crystals to form. So they form very, very fine, smaller grains. Basalt is an example of an extrusive rock, and it's finely grained due to that rapid cooling process. But that doesn't mean that we don't get any minerals forming in that rock. It just means that the minerals present are going to be very, very, very small crystals. Usually not large enough to facet by any means, but there may be small crystals present. Some basalts can contain corundums, zircons, and garnets, but they're not going to be large enough to facet, and they're not going to be gem quality. One volcanic rock that is interesting to us as gemologists, and we're not going to go into a lot of detail in Gem 1, is kimberlite. Kimberlite pipes are the transportation mechanism that brings diamond crystals to the Earth's surface. Notice I said transportation mechanism, because the kimberlite pipes is not where the diamond crystal grows or originates, but it's simply the mechanism that brings the diamond crystal from deep within the Earth's structure, or sometimes 70 kilometers beneath the Earth, up to the Earth's surface. Intrusive igneous gemstones. The molten rock solidifies within pre-existing other rocks. And so it is sheltered by those pre-existing other rocks and is allowed a lot of time to cool down. And the longer time that it's got to cool down, the more time that the chemical elements within that rock have got to settle out and to form nice little lattice structures and form those crystal lattices. So we tend to see much larger crystals forming within the intrusive igneous rocks. And particularly if we look at one particular type of intrusive igneous rock named a pegmatite. Pegmatites are internal bodies of intrusive igneous rocks that can be several meters to several kilometers large, depending upon the particular pegmatite, and can contain very, very large crystals that are several meters long or longer. So the intrusive igneous rocks, with the length of time on cooling and the cavities that allow the gemstones to grow, the room to grow, can result in very, very large crystals forming. Granite is a type of intrusive igneous rock, and granite is comprised mainly of quartz and feldspar. Sometimes can contain other minerals such as mica or hornblende. We have one particular rock that we look at in ornamentals that we like students to identify that is technically a granite. Putting you on the spot, name the rock. It's pink and green and mottled. Unakite. So unakite is comprised of pink orthoclase feldspar and quartz. Quartz and feldspar are a granite. So it's a coarse grained rock. But in addition to the quartz and the feldspar, we also have the epidote, which is a green colour. So an intrusive igneous rock. So the slow cooling creates crystals of different minerals as they can form at different temperatures as well. Minerals of the pegmatite group are among the last to be formed and can form in veins or in kind of plutons and internal cavities. We're going to talk about pegmatites as a separate discussion point after we talk about the basic types of rocks, because pegmatites are really, really important to gemstone forming rocks. We find a lot of really important gemstones in pegmatites. 9 o'clock, got half an hour, got to keep an eye on that time. Okay, so the type of gemstones that we find in intrusive igneous rocks include beryl, chrysoberyl, corundum, diamond, garnet, feldspar, peridot quartz, spinel, topaz, tourmaline, zircon. So quite a lot. Most of those are pegmatite minerals. Beryl is listed here, but for the purposes of pegmatites, we don't tend to see emeralds in pegmatites, but other beryls you do see. And the reason is the chromium content. And that's more of a discussion point for Gem 2. We don't want to overcomplicate the chemistry in first year beyond the basics. Igneous rocks can be transformed into sedimentary rocks via a weathering process. So intrusive igneous rocks that are buried deep within the Earth's surface need some mechanism to bring them to the Earth's surface. So we see things like earthquakes, plate tectonics, shifts in plates may rise rocks or bring rocks closer to the surface, while at the same time bringing or forcing rocks further down within the Earth's crust. So vice versa. Processes of subduction may take older rocks down back to the magma, but where we get rising actions, we get rocks that were buried deep within the Earth's surface being brought closer, and then erosion may start to break up those rocks into smaller sediments and relocate them. So we get gemstone deposits which are revealed by that process, or we get gemstones being removed and scattered down scattered down river systems and riverbeds. So seismic activity and movements in oceanic or continental rocks is a very important mechanism for bringing those rocks to the surface and gemstones to the surface. And remembering from earlier in the presentation, we said that gemstones tend to form at around 40 kilometres beneath the Earth's surface. So there needs to be some pretty big seismic activity to bring those stones up 40 kilometres. Forms of weathering and erosion. So we have the actions of wind and water, which can break up rocks into smaller pieces and sediments. But sedimentary rocks are formed when small particles of older pre-existing rocks are deposited elsewhere. So the wind and the water break up the rocks into small sediments. They're carried away and they're deposited, which means they fall down to the ground, and they'll fall in layers. And then those layers will get compacted and they'll make new rocks. So sedimentary rocks can be recycled. Should read what I Once that process of forming sedimentary rocks has been completed, then we have an existing rock, which then is available to be changed into a new rock. And the next process that we're also going to talk about, sedimentary rocks can be recycled into metamorphic rocks by applying heat or pressure to them to change the nature of their structure. Anyway, so sedimentary rocks, small and large sediments are created by weathering of existing rocks. The eroded particles are transported by air or water and deposited in layers. So I said all that, that is good. Compacted over time, these processes take a lot of time to occur. Once a rock has been either eroded, sometimes the rock can also be dissolved in the water. Particles are transported, deposited, they become new rock. Particles can fall in the water, deposited in lakes, oceans, or old river channels. They're not actually deposited in old river channels. They were deposited in river channels many moons ago, where the water is now evaporated and is now what we refer to as an old river channel. And some of these old river channels can be very economical for us in retrieving a lot of the minerals that were deposited along when it was a free-flowing river. Rock minerals can be dissolved in water and also deposited, filtering through other sediments to become cementing material for new rocks. The weathering occurs when rocks are exposed to the atmosphere, so to wind, water, or living organisms within the Earth's surface. Rocks may break apart without substantial change to their chemical structure, and this is called physical weathering. So changing to chemical structure means to break down the rock into its constituent elements. If we're not changing the physical structure, it just means that we're taking one big rock and breaking it into many smaller rocks. But those smaller rocks are now lighter and transferable and easy to transport to another location. Chemical weathering, as opposed to physical weathering, occurs when some of the minerals within the rock break down, and they may be dissolved and combined with water over thousands of years and may form other new rocks. And then some of those new rocks may also be easily eroded as well. Biological weathering occurs when organisms are directly attacked by the rock. And this can be the result of the growth of trees or plants in joints and seams of rocks. I didn't actually have time to include any new photos in this presentation, but one of the things that I was really interested in when we were in Vietnam, Adele, did you notice when we took that boat trip through the cave systems, how many of those cave entrances, we had all of these rocks that had large fractures. The rocks were in layers with big fractures through them, and they all had these really interesting trees with these long tree roots that were growing along the fractures. And there was evidence of these rocks breaking away where those tree roots were. And I just thought it was really, really interesting to see all of those trees trying to grow in those fractures. And you could see as the tree grew up that those roots would become bigger and force that fracture open more. So an example of biological weathering with trees attacking rocks. Attack of the trees. So deeply buried sedimentary or igneous rocks may be subjected to tectonic forces that change their structure. I feel like we've said that already. Due to the high temperatures or being squeezed and folded by very high pressures or both. Sometimes really interesting to walk around and just notice the rocks around you. There's a couple of really interesting cuttings around Melbourne where you can see rocks that have been folded. And the only way that rocks can be folded is through that process of undergoing that metamorphism. So the heat and the pressure reform existing rocks. They make them a little bit plastic. They make them soft enough to be able to move. So as plates move in one direction, it may cause those rocks to fold a little bit. No, I'll just skip over that. Okay, so we're back to igneous rocks again. I feel like I need to reorder this PowerPoint just a little bit. So back to igneous rocks, remembering that igneous rocks are formed by magmas, and the intrusive igneous rocks solidify underground to form granites. The extrusive igneous rocks solidify on the surface to form basalts. The texture of the igneous rocks varies depending on how rapid the cooling is. So more rapid cooling, more fine-grained texture. Cooling over a longer period of time, you get a more coarse-grained texture and the ability for larger crystals to grow. Intrusive igneous rocks are usually crystalline, but the igneous rocks usually have a massive appearance to them. They can have a homogeneous texture with interlocking crystals. This also describes the appearance of pegmatites, and later on during the presentation, I've got some really cool photos of pegmatites with garnet crystals growing in the pegmatite material. And you can see the homogeneous texture of that pegmatite material. When the igneous rocks are high in silica content, we call them acidic. And acidic means that they have a lot of free quartz in them. And igneous rocks with free quartz tend to form granites. When they're low in silica, they have no free quartz, and we call these rocks basic. So it would be nice to remember that the silica content is related to what types of minerals may be able to form in those rocks, and that rocks with a high silica content will have granites, and rocks with a low silica content have no free quartz and are basic. Sedimentary rocks are generally made up of deposits laid down on the Earth's surface by water, wind, or ice. They are always laid down in layers, so sedimentary rocks tend to have that layered structure. Because this process happens while animals are living around that area, they tend to capture living animals or dead animals in that process. So we can find really good fossils in sedimentary rocks. We won't find fossils in igneous or metamorphic rocks. And the sediments are caused from eroded fragments of other rocks that are cemented together. and that process is called clastic sedimentary rocks. So sedimentary rocks will be divided into two types of rocks: clastic sedimentary rocks and non-clastic sedimentary rocks. So clastic sedimentary rocks are rocks where the fragments have been cemented together. Sedimentary rocks that are non-clastic result from materials that are dissolved within the water rather than fragments of rocks that are glued together. So things like, and I'm looking at the screen, salt deposits where the water is evaporated and the salt crystals are left behind is a good example of a non-clastic sedimentary rock. So materials that are dissolved in water and form rocks in that way. Peat is another example of a non-clastic sedimentary rock, being biological in origin. So carbonates such as limestone also occur from precipitation from an aqueous solution. And organic origin include things like coal and peat and other rocks formed from the fragments of shells that can accumulate in layers. Metamorphic rocks formed when existing rocks are subjected to extreme temperature and or pressure, and that's going to alter mineral composition and texture of the structure of the rock. It can mobilize elements to migrate between rock structures, which enables new crystals to be formed. So we get a lot of gemstones that are metamorphic in origin because the elements have been shifted around and jolted around and have been transformed, and through the crystallization process, new crystals are grown out of that surrounding rock environment. Metamorphic rocks include schists and gneisses, whose component minerals tend to segregate into separate bands, giving a layered appearance. Emerald is a really good example of a metamorphic rock that forms in schists and gneisses. Metamorphic rocks, because of the heat and pressure that they're subjected to, tend to be really hard rocks. But they also go through that process of recrystallization. But they're hardened due to the extreme temperatures. So this is a picture that I found. This is not from Victoria and not a picture that I've taken, but that shows the folded nature of the rock because of the metamorphic actions. If anyone goes for a walk around the Tan or goes for a run around the Tan, some of the cuttings along the edge of the Yarra show that kind of folded nature to the rocks. And if you go out on the freeway, the Eastern Freeway, through some of the cuttings through there, you can also see the foldings of the rock, which can be really cool. This is an example of a spinel that's embedded in its host rock, which is marble, which is a metamorphic rock. And this example is from Mogok in Burma. The spinels from Vietnam, from Luc Yen up in the mountains in the north, are also a marble deposit, so they're also metamorphic rock. And you get these really beautiful spinel crystals, and sometimes the corundum crystals growing out of this marble bedrock. So a little bit about Mogok, because that specimen that was photographed was from Mogok, just to try to give you an idea of the chain of events that leads to these gemstones forming. So Mogok's history, originally Mogok used to be underwater. So the original rocks of Mogok originally were broken up and formed sediments and formed sedimentary rocks. So we had sedimentary rocks that were laid down in layers. After that sedimentary process, the next process that happened was that we had an intrusion of magma that formed intrusive igneous rocks. So we've got a mixture of both sedimentary rock and intrusive igneous rocks. The third process that happened was that there was alteration of those rocks from a metamorphic process through heat and pressure. And that changed the nature of those sedimentary rocks and igneous rocks and mobilized some of those elements to form new rocks. And some of the elements that were present were able to recrystallize to form the gemstones such as spinel and ruby that we find from Mogok. That process introduced the chromium, which produces the red colour of the ruby and the red colour of those spinel crystals. So the tectonic plate activity was the last piece to this equation, which pushes the plates against each other. And while some plates may be forced down back towards where the magma is, that process is called subduction. Some of the plates were forced higher into the mountain ranges, and the plates that were forced higher into the mountain ranges were then once again exposed to a weathering process, which uncovers or reveals the gemstone deposits, and in some cases loosens those gemstone materials and redeposits them elsewhere. So when we were in Vietnam last month, some of the locations that we went to up in Luc Yen, we went to a mining area, and this mining area in Luc Yen, high in the mountains, was a rice paddy. And they were farmers growing rice in the rice paddy at the base of these marble mountains. And the marble mountains have got water travelling through the mountain that's eroding the rock, and that rock is coming down bit by bit with sediments and falling down to where they're growing the rice. So there was a group of about 6 men in the middle of the rice paddy who had a small clearing of a couple of metres, and they were sifting through the topsoil to find any of the spinel crystals that had washed down from the mountain that was just to the side of the rice paddy. So this is kind of the rock cycle repeating itself, recycling rocks, and then revealing some of these crystals and making them available to us to be able to find. Okay, so the limestone, which is the sedimentary rock, gets changed to marble through the metamorphic process. And the interactions between the constituents of the igneous rock and the constituents of the sedimentary rock form these new metamorphic rocks and release some of those elements that come together to crystallize these gemstones. For the stones in Mogok, the rubies are thought to have formed during a period of about 18.7 million years ago, is when those rubies formed. Okay, on to pegmatites. What have we got? 9:15. We can do this, Adele. Okay, so pegmatites are one of the most important sources of gemstones. They are a type of rock formation that gives rise to gemstone crystals forming, but they also have an economic value to them. They're a highly concentrated source of gemstone because of the type of rock formation that they are. They're an intrusive igneous rock, which means they're formed by the solidification or the cooling down of rising magma. And they're intrusive, which means that the magma solidifies and cools down within the Earth's surface. The pegmatites that give rise to gemstones tend to be a plutonic body. They tend to be almost balloon shaped in their formation, but we can get different sizes of pegmatite bodies. Pegmatites are very recognizable by their coarse texture and different combinations of crystals and gemstones and rocks that are present within them. Because of the intrusive nature, because they're intrusive igneous rocks, they take a long time to cool down, which gives the crystals a long time to crystallize, which means that they have larger crystals and gives the overall appearance of the pegmatite that kind of coarse nature, because we get lots of different sized crystals and rocks. This is an example of a pegmatite that contains garnet and tourmaline, and it's within a mica schist. This is referred to as a graphic pegmatite because of the pattern of the tourmaline, which are these kind of long bladed minerals, and the garnets, which are more these rounded crystals, but you can see that there's a little bit of geometric shape to them. Not all pegmatites that contain large crystals contain gemstone quality crystals. It's just a very, very small proportion, maybe 1 or 2% of pegmatites contain gem quality crystals, but pegmatites are known for producing large sized crystals. So they're an important source of industrial quality minerals because only 1 or 2% of them are gemstone quality, but a number of the minerals within pegmatites can be ground down to extract the rarer minerals that are contained within them. So feldspars, sheet micas, and beryllium are some of the elements or some of the resources that can be extracted from pegmatites. Other things that can be extracted from pegmatites that are a little bit topical at the moment, lithium, for lithium batteries. I was reading last year or the year before some of the finance magazines, because, you know, why not? They're talking about mining companies in Australia that were prospecting for lithium for battery use in Western Australia, and they were talking about the lithium-rich pegmatites in Western Australia. And as a gemologist, I've gone, whoo, pegmatite, gemstones. They also mentioned another word, spodumene. And I've gone, wow, we've got spodumene in Australia? That's kind of cool. Does anyone know what gemstone spodumene is? Kunzite. Yes. So mentioning that only 1 or 2% of pegmatites contain gemstone, gem quality minerals. Australia doesn't have any gem quality spodumene crystals, so we can't actually mine kunzite in Australia. But we've got a lot of spodumene that's non-gem quality, and they're grinding it all up for the lithium to produce lithium batteries. And they're getting it out of pegmatites. So pegmatites occur worldwide, and we get a really impressive, diverse range of minerals and elements contained within pegmatites. And pegmatites are a really good way that the earth, what's the word that I wanted to look for? Concentrates, that's the word that I wanted, concentrate some of these rarer elements. And these rarer elements might not just be used in gemstones, but they're extracted for a whole lot of other industrial applications. But only about 1% of pegmatites contain gem quality crystals. So pegmatites comprise a number of minerals. Primarily, the pegmatites that contain gemstones tend to be granite pegmatites. So because they're granite pegmatites, they contain quartz and feldspar, and then other types of minerals as well. And the other types of minerals that they contain include tourmalines, topaz, garnet, spodumene, because it's lithium, scapolite, beryl, but not emerald, because we don't get chromium mobilizing within pegmatites. Apatite, fluorite, and zircon are just a few of the pegmatite type minerals. Some famous locations for gem-bearing pegmatites include San Diego County in California, Minas Gerais province in Brazil. We've got northern Pakistan and neighbouring Afghanistan, and we've got the Ural Mountains in Russia. The Ural Mountains in Russia, well-known location for demantoid garnet, Northern Pakistan and neighbouring Afghanistan, we're seeing really fantastic large crystals of tourmaline, of topaz, and of beryls such as aquamarine coming out of those areas. Brazil, almost every mineral comes from that area of Brazil. They get basically everything. San Diego County in California, I really want to say that's where the Little 3 mine is for the spessartine garnet. Adele, is that in San Diego? No.
idea.
No idea?
No,
Oh,
no.
okay, then I'm going to confidently say that's where you get the spessartine garnets from.
Not
In America.
necessarily.
So key concepts of pegmatites, they have variable texture and coarseness. So they're intrusive igneous rock, they take a long time to cool down, and all of those elements start forming different rocks and different minerals, and over time they form larger crystals or can form smaller crystals, and it's this large body of interesting stuff. All these different crystals grow together, so they have an interlocking type structure. So similar to that graphic pegmatite that we saw with the tourmalines growing at all different angles within that rock structure, we get this kind of interlocking coarseness. Pegmatites can be quite complex, and they can show different zones depending on the temperature of formation and the time of growth. Pegmatites also show a differentiation process whereby the heavier elements will settle out of the melt first and solidify into hard rocks. And those rocks are going to be very rich in iron content and a darker colour. But once they remove the iron content from the original melt, the remaining melt becomes progressively concentrated in the other elements that may have been rarer in the magma, but start to become very concentrated in the pegmatites. So things like the lithium that goes into the spodumene, or the boron that goes into the tourmalines, gets very progressively concentrated. But because of this, because of that differentiation process, the pegmatites can appear to be segregated. So as the composition of the melt changes, as certain rocks crystallize first, the nature and appearance of the pegmatite is going to change because the crystallization of different rocks changes through the body of the pegmatite. There's also variability in overall geometry and size of the pegmatite. Is that a question at home?
Yes, I have this book,
Okay, I can't see that here.
and it says that there is actually 3 or so different locations in Australia where you can get kunzite. One of which is Ravensthorpe, Mount Marion, south of Kalgoorlie, the McPhee Range in Western Australia, and there's a mine around Perth somewhere, Greenbushes Tinfield.
Okay. There you go. And does it say that you can actually get large size crystals, or?
It sometimes forms very large crystals, is all it says.
Okay. I'm unaware of any gemstone quality crystals from that area.
Yeah.
But yeah, there's apparently quite a lot of mining for the lithium by smashing up those minerals.
These are really good books. I highly recommend them. It's like turn down this dirt road for 2.5 Ks and then turn at an anchor, and yeah.
Yeah. So pegmatites, because the chemistry changes during the growth process, they can have very diverse range of crystals, but also depending on the temperature and growth environment, the size of the crystals can also vary. But we can get very, very, very large crystals forming in pegmatites that can be up to many meters long. This is an example of some garnet crystals in a pegmatite. So you can see the pegmatite rock itself is very homogeneous. It's very same all the way through. but then we get these really beautiful large garnet crystals, a lot of which show really nice crystal structure. So it's had enough time and room for those crystals to grow symmetrically and to be able to form those nice crystal shapes. This is another example of a granite pegmatite, a rare one because it does contain emerald, and this one comes from North Carolina in the United States. So granite pegmatite, so it contains quartz and feldspar, but the black crystals here are tourmaline, and it says the green crystals are emerald. So there you go. So pegmatites, as the large igneous body cools, the heavier elements will settle out first and form the first layer of rocks. And they tend to be rich in iron. But once the iron's been taken out of the equation, the overall mix of the melt is going to change. And so the nature of the rocks that crystallize out over that time is going to change. A small percentage of the melt is going to concentrate some of the rarer elements that are required for some of the most beautiful gemstones. The other thing that's required in pegmatites is cavities. So the groundwater of the magma can contain what's referred to as volatiles being water or aqueous solutions. The water is not compatible with some of the most basic rocks, so it's not incorporated into the basic gem-forming rocks, but because it's not incorporated, it gets left out and it starts to be more concentrated towards the top of the pegmatite body. And those little pockets of water is what forms the little cavities that allow the room for the crystals to grow. The crystals also require a hot aqueous solution to be able to grow in, and that's often referred to as the hydrothermal process or hydrothermal growth process. Scientists, in learning about the processes in which rocks grow in within the Earth's surface, have then been able to replicate some of these processes in the lab. So one of the methods that we have to grow crystals is also called the hydrothermal process, and you'll learn about that in Gem 2. But some of the gemstones, such as emerald, are grown via a hydrothermal process, which mimics this process that happens within the Earth's surface. So cavities will only form if you've got water present and if that water separates out from the rest of the rock. So separation of that fluid phase is only possible if the melt contains water to begin with, which I think is kind of a little self-explanatory. And then under favourable physical conditions, that aqueous fluid will form those cavities, and then that gives the room for the crystals to grow nice and large. A key to the formation of the gem species is what's called progressive fractionization of the melt. So the heavier elements dropping out and forming the first process of rocks, but then the remaining melt becoming richer and richer in rarer elements, while also having that water present for those crystals to grow in. So a small number of the rarer elements get progressively concentrated in the pegmatite as the pegmatite cools and crystallizes. So the rare elements include things like lithium, beryllium. Beryllium is important for chrysoberyl and for beryl. Boron is important for tourmaline. We've got lithium, which is important for the spodumene, as well as volatile materials such as water, fluorine, which is important for things like topaz. So all of these become a melting pot for really beautiful crystals to grow in. So as the remaining fluids become progressively richer in these substances and these elements, we've also got silica present as well. So they tend to form silicate minerals, or they may form oxides depending on how much silica is present. So for example, beryl is a beryllium aluminium silicate, but chrysoberyl is a beryllium aluminium oxide. So the resultant crystal that we get depends on the chemistry of the mix. If you've got the beryllium and the aluminium and you've got silica, you're going to get the beryl crystal forming, but if you've got the beryllium and the aluminium but no silica, you're going to get the chrysoberyl forming. So it depends on the chemistry of the melt. So these rarer elements, such as the boron and the lithium, are incompatible with earlier stages of the rock formation process because of the size of the element, or maybe because of the valency of the element. So towards the end of the crystallization process, the remaining molten portion is very rich in the elements needed to make our gemstones. And these tend to crystallize at the top of the igneous body, which concentrates those crystals near the surface of the earth, which makes it really easy for us to kind of get to. So it's a very nice economical deposit, rich of gemstones. And the chemistry of the melt determines what crystals grow there. So if we've got beryllium, we'll get either chrysoberyl or beryl. If we've got boron, we'll get tourmaline, and etc. I'll skip over that. Gem-bearing pegmatites are rare. So less than 2% of total pegmatite population produces gem minerals. And of these, less than 1% contain cavities required to grow large crystals. And so pegmatites, only 5% of the volume are cavities and 95% is massive rock. This is in Mexico. These little people dressed in orange hazmat suits are walking around this giant crystal cave, which was a cavity in a pegmatite. So we can get very, 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 very large crystals. This is an example of a topaz crystal that has come out of a pegmatite in Brazil. And these are a couple of topaz crystals from Brazil with a small child sitting next to them for size comparison. I'm going to leave it there at gravel deposits. We've really only got about 10 slides left, but we'll pick it up next week. And then next week we're going to be looking at the spectroscope, which is the last instrument that we're going to look at. And then we're going to start looking at quartz in detail. So this is the tail end of the scientific part of your qualification. From next week onwards, we're going to start looking at gemstones in more detail and the process that we go through to identify them and their identifying characteristics, how they can be treated and how they can be synthesized.
Thank you.